Think about walking into a room full of strangers. Before you speak to anyone, 1,000 different futures are possible. You might make a new friend, have an awkward chat, or be ignored completely. All those potentials exist at once. But the moment you choose to say hello to someone, you collapse all those possibilities and start writing one specific story into existence. This isn't a philosophy, it's the central mystery to quantum mechanics. In next few minutes, we'll explore the science that stumped even Einstein, and we'll ask the biggest question of all. What does it really mean to look, to observe? Imagine a single unstable atom. Quantum mechanics tells us that after a certain amount of time, say 1 second, there is a 50-50 chance that it will have decayed. But what if you don't leave it alone? What if you keep observing it? According to mathematics, just before measurement is made, the atom doesn't exist in one definite state. Instead, it exists in a superposition, a ghostly overlap of both decayed and not decayed at the same time. What if you try to watch the atom decay by measuring it constantly, like observing it 1,000 times a second? Common sense suggests that you would eventually catch it in the act of decaying. But that's not what happens. Each time you measure the atom, you force it to settle into a single outcome. If it hasn't decayed yet, the measurement collapses its cloud of possibilities back into a definite, not decayed state, effectively resetting the clock. So think about it. By observing the atom again and again, you can actually prevent it from decaying at all. It's the ultimate quantum version of washed pot that never boils. This is the observer effect. The moment you look, reality isn't just revealed, it's altered. And understanding why this happens remains one of the deepest, unsolved mysteries in physics. Quantum mechanics seems to play by two completely different and conflicting set of rules. Rule number 1 is the Schrödinger's equation. This is the master equation for quantum mechanics. According to this equation, the system evolves smoothly and predictably as a wave of possibility, a superposition in every potential state it could be in. Rule 2 is what physicists call the collapse of the wave function. This rule jumps in whenever a measurement happens. The instant you interact with the system to get the information about it, that smooth wave evolution just stops. The superposition of all possibilities violently and randomly collapses into just one of them. You see the conflict? We have got a predictable wave on one hand and a random collapse on the other. They just don't fit together. A measurement, after all, is just a physical interaction between particles. Why should this one type of interaction play by a totally different rulebook than everything else? This is the measurement problem. It's a cascade of questions that poke at the very nature of the reality. First, the problem of outcomes. Why do we only ever see one outcome? The math describes a world where atom is both decayed and not decayed, but we only ever see one or the other. Where did the other possibilities go? Then there is a problem of preferred basis, which is a fancy way of asking why do measurements give us simple and clean answers. We don't ever measure it in some strange combination of states, like a mix of position and energy. The theory allows for countless ways to measure something, but the nature seems to choose only one. This paradox was brilliantly and famously captured by physicist Erwin Schrödinger and his unfortunate cat. Imagine a cat sealed in a box and a vial of poison. The poison gets released if a single radioactive atom decays. According to Schrödinger's equation, until we open the box and measure it, the atom is in a superposition of both decayed and not decayed. But since the cat's life is tied to the atom, the cat must also be in a superposition, simultaneously alive and dead. The measurement problem is the question of what happens between the quantum maybe of the atom and the classical yes or no of the cat. For decades, many physicists just threw up their hands and adopted a shut up and calculate attitude. The rules worked for making predictions, so why worry about what they meant? But that's not good enough. It leaves a massive hole in our understanding that the solid, definite world we experience grows out of a foggy, probabilistic quantum realm. This brings us to one of the most misunderstood words in this science: observation. In everyday language, observing usually means a person looking at something, watching it with their eyes. And it's natural to carry that intuition into quantum physics. But that intuition turns out to be misleading. When physicists talk about an observer collapsing a wave function, they are almost never referring to a conscious human mind. An observer doesn't have to be a person. It doesn't even have to be alive. In quantum mechanics, an observer is any physical interaction that causes information about a system to escape into the environment and leave a trace behind. That trace can be something as small as a photon bouncing off a particle, a detector needle shifting, or a tiny change in electric or magnetic field. Once that information exists anywhere outside the system can no longer behave as a superposition. Think of the wave function, the cloud of possibilities, as a secret. As long as the secret is perfectly contained, the superposition survives. The moment the information about the particle spreads into wider world, the superposition is destroyed. The device checking the atom isn't a neutral witness. It's more like a careless messenger. To find atom state, it has to interact with it. And that interaction always leaves a mark. A photon is scattered. A magnetic field shifts ever so slightly. That single interaction links the atom to the detector to the lab, and the lab to the surrounding air. And suddenly, the information about the atom's state is spread outward into the world. The fact that atom has not decayed is no longer private. It's written into the environment. And once that information exists out there, the alternative that the atom has decayed can no longer survive. The secret is gone. The wave function has collapsed. So observation in quantum world is information leaking into the environment. And once observation is understood as that, a clear physical process comes into focus. The modern scientific understanding of this process is called quantum decoherence. It explains why quantum superposition are so fragile and why, in our everyday world, quantum weirdness vanishes almost instantly. Decoherence shows us how a system's many possibilities becomes spread out and effectively lost to the environment, leaving behind a single stable reality we experience. Imagine a single perfectly vibrating violin string in a totally silent room. That's our quantum state in pure superposition. Now, open the door to a busy street. The noise of the traffic, the rush of the air, all those vibrations of the environment, they all interact with this string. Its pure, coherent vibration is quickly drowned out and lost. It decoheres. And this is what happens to quantum systems. They are incredibly fragile. A single stray photon or air molecule is enough to measure the system and shatter its delicate superposition. Our world is very, very noisy place. Big things like us, cats or baseballs are being relentlessly bombarded by trillions of particles every nanosecond. They are being measured by their environments so constantly and so fast that they can never maintain a quantum superposition. They are forced into a definite classical state. This physical reality is the true meaning behind reality breaks the moment you look. It's not reality is shy, it's that the reality is a delicate web of interaction, and the look is to touch that web, causing ripples that turn possibility into fact. While decoherence tells us how quantum possibilities get narrowed down, it doesn't still answer the deepest question. Why do we experience this one specific reality out of all the ones that could have been? This is where physicists, without a complete story, wander into the wild territory of interpretation. These theories aren't proven facts, but different philosophical maps for making sense of the bizarre quantum rules. One of the most mind-bending theory out of that, and yet it is weirdly elegant, is the many-world interpretation proposed by Hugh Everett III. It makes a radical claim. The wave function never collapses. There is no special measurement rules. Instead, every single time a quantum measurement could happen, the entire universe splits into multiple branches. In each branch, a different outcome becomes real. When a measurement is made on the unstable atom, the universe splits. In one universe, you measure it as not decayed. In another identical universe, a copy of you measures it as having decayed. Schrödinger's cat, universe splits. In one branch, the atom decays and the cat is dead. In another, it doesn't. There's no collapse, just a constant branching of realities. Every possibility happens somewhere. We just happen to be in one of those branches with no way to see the others. Then on the complete opposite side of the spectrum, you have most controversial and tantalizing ideas of all. The consciousness causes collapse hypothesis. This interpretation, linked to physicists like John von Neumann and Eugene Wigner, takes the word observer quite literally. It proposes that the one thing truly unique about measurement is that it eventually gets registered by a conscious mind. Therefore, it is consciousness itself, and only consciousness that can collapse the wave function. In this view, the detector, the computer screen, even the light hitting your eyeball, all of that stays in a state of superposition until the information hits your brain. At that moment, and only at that moment, the reality snaps into place. Finally, there's a powerful way to think of all this, the simulation analogy. It isn't the formal theory, just a thought experiment. What if the universe is like a super advanced video game, a simulation? To save the processing power, the game's engine wouldn't render every single detail of the whole world all the time. It only renders what the player is looking at right now. The rest of the world might exist just as data, a set of probabilities. When the player turns around, and the graphic engine instantly renders the scene, collapsing the data into visual reality. In this analogy, the simulation analogy, measurement is like a player looking. The universe doesn't bother keeping a definite reality for every single particle all the time. It just holds them in a state of potential, a wave function, and only renders a real outcome when an interaction forces it to. Again, this is just a metaphor. There is no scientific evidence we live in a simulation, but it's a powerful way to think about how reality might only become concrete when it's observed. We have gone from a single experiment with atoms to huge parallel universes. These ideas are designed to stretch our brains and challenge our most basic assumptions about the world. If this is expanding your mind, hit that subscribe button to keep exploring the big questions with us. And I want to hear from you. Drop a comment below. What interpretation makes the most sense to you? Do you think decoherence explains it all? Or are we living in one branch of many worlds? Or is there another idea you find more compelling? Now, it's at this point that some people take dangerous leap. They hear observation creates reality and conclude that they can think their way into a new car or a lottery win. Let's be crystal clear that it is a pseudo-scientific twisting of quantum physics. The observer effect is a real physical thing, but it does not mean your thoughts are magically collapsing wave function into your day-to-day life. Quantum effects are incredibly fragile and are completely washed away by decoherence at any scale larger than a molecule. You are a big microscopic object and you're not in a superposition of being rich and poor. However, to dismiss any connection to our lives would be to miss a profound philosophical lesson sitting at the heart of quantum mechanics. The real takeaway isn't about magic, it's about the power of interaction and attention. The universe at its core is a dance between what could be and what is. Interaction is the choreographer of that dance. While you're not collapsing an atom's wave function with your brain, the principles of observation have powerful parallel in our own lives. Your life is defined by what you choose to interact with. Your attention is your most powerful tool for interaction. Think back to that feeling of being stuck in a loop. That loop isn't a quantum state, but it is a psychological one. It's a pattern that gets reinforced by observing, by paying consistent attention to the same thought, to the same limits, to same triggers, to same old story about who you are. Your focus acts as a filter for your reality. What we consistently focus on feels more real, more solid in our lives because our attention guides our actions, our perceptions, and the opportunities we are able to even notice. The observer effect in our human experience is this. By consciously choosing where to place your focus, you're choosing which version of reality to engage with. When you decide to learn a new skill, you're interacting with a potential future self that has that skill. When you choose to forgive someone, you are interacting with a potential relationship that is free from resentment. You aren't magically creating these things from thin air. You are interacting with the potentials that already exist, and through your focused action, you are making one of them more real than the others. So let's bring it all back. Reality doesn't break the moment you look at it. In a way, it forms. The act of measurement, of interaction, is the bridge from the ghostly realm of quantum potential to the solid classical world of definite experience. The universe isn't just happening to you, it's happening through your constant interactions with it. From the smallest particle to biggest idea, reality is a participatory process. The paradox of the observer reminds us that we are not just a passive audience watching a movie, we are active participants in the unfolding of reality. And while we may not be able to choose the quantum state of an atom, we absolutely can choose what we observe in our own lives. We can choose which potentials we engage with, which thoughts we give power to, and which futures we decide to interact with. The real question isn't just what we are looking at, but how you choose to see it. Thanks for watching.